A sudden, powerful burst of radio waves from a distant galaxy rips through the silence of space. This is just one of the strange cosmic messages reaching our planet, signals that defy all our expectations. We are about to embark on a journey to the very edge of our understanding, exploring 25 of the universe's most baffling transmissions. You will discover signals that repeat with clockwork precision, whispers from the dawn of time, and blips of energy so intense they could power our world for millennia. What caused the legendary WOW signal that vanished without a trace? And why does a distant star seem to be surrounded by a structure of unimaginable scale? When you look up at the night sky, do you ever feel a sense of profound mystery? That single, powerful burst of radio waves was not the first time we were caught off guard. Decades earlier, a volunteer astronomer named Jerry Amon was scanning data from the Big Ear radio telescope at Ohio State University. He was reviewing a printout from August 15, 1977, when his eyes landed on a sequence of letters and numbers so extraordinary he circled it and scribbled one word in the margin. Wow! The signal was a narrowband radio burst, the exact type scientists predicted an intelligent civilization might use. It came from the direction of the constellation Sagittarius, and for 72 glorious seconds, it overwhelmed the telescope's receivers. The now famous code 6EQUJ5 was actually a measure of its intensity, a sudden, screaming peak in the cosmic silence that then vanished completely. The Big Ear telescope was fixed in place, relying on the Earth's rotation to scan the sky, so it could only observe that specific point for 72 seconds. We have never heard it again. Despite countless searches aimed at that same patch of sky, the WOW signal remains a perfect, singular event. Its one-time-only nature is what fuels the deepest speculation. Was it a message, a beacon that flickered on just long enough to be noticed? Or was it the catastrophic collapse of an alien megastructure, a final, fleeting shout into the void? It stands as a haunting ghost in the machine of astronomy, a reminder that the universe might be speaking in whispers we are only just learning to hear. The ghost of the WOW signal had barely faded when the cosmos delivered an even greater puzzle, one that broke all the rules. For years, astronomers believed the brilliant flashes known as fast radio bursts were cosmic one-hit wonders, colossal explosions that tore through space and then vanished forever. That assumption was shattered by a single object, FRB 121102. This was not a solitary shout into the dark. It was a repeater, nestled in a tiny dwarf galaxy an astonishing 3 billion light-years away. This source behaves like a temperamental cosmic lighthouse. It erupts without warning, sending out erratic blasts of energy so powerful that each one releases more energy than our sun will emit in 80 years, all compressed into a few thousandths of a second. Then it falls silent for days, weeks, or months, only to suddenly flare up again in a storm of unpredictable activity. Pinpointing its home galaxy was a monumental achievement, finally giving one of these phantoms an address. But what kind of natural object could possibly produce such frantic, repeated outbursts? The leading suspect is a magnetar, a type of neutron star with a magnetic field so intensely powerful it could erase your credit cards from halfway across the galaxy. Theorists suggest that a young, hyperactive magnetar might occasionally crack under the strain, its crust snapping and releasing titanic flares of radio waves. Yet the sheer raw power and the baffling irregularity of these bursts have left the door open for more speculative ideas. Could we be witnessing the intermittent powering up of unimaginably vast alien technology? A cosmic engine flickering on and off as it performs tasks beyond our comprehension. FRB 121102 forced us to rewrite the textbook, proving that the universe's most violent phenomena are not always final. Some mysteries are patient, and they are waiting to speak to us again. The erratic chatter of the repeater forced astronomers to confront a startling truth. These signals were not flukes. and the proof had been hiding in plain sight for years. The story of the fast radio burst truly begins not with a live detection, but with a historical echo. In 2007, an astronomer named Duncan Lorimer was sifting through old data from the Parkes Radio Telescope in Australia, archives recorded back in 2001. Buried within that mountain of cosmic noise, he found something that should not have been there. It was a single, monstrous spike of energy so powerful it saturated the telescope's receiver. This event, now known as the Lorimer burst, lasted for just 5 milliseconds. In the blink of an eye, it released more energy than our Sun emits over 300,000 years. The scientific community was deeply skeptical. How could something so impossibly bright exist for such a fleeting moment? Many dismissed it as a one-time glitch, perhaps a malfunction of the telescope or even a signal from a passing satellite. But Lorimer and his team stood by their data. They had uncovered the very first official fast radio burst, a ghost from the past that would not be ignored. This single, 5-millisecond blip was the spark that ignited an entire new field of astronomy. It forced researchers to start listening to the universe in a new way, to build instruments sensitive enough to catch these cosmic will-o'-the-wisps. The Lorimer burst was the original template, the proof that the cosmos was capable of screaming in flashes too quick for the human mind to even register. It was the quiet beginning of a very loud mystery. While the Lorimer burst was a ghost from the distant cosmos, another signal seemed to come from right next door. In 2020, the world of astronomy buzzed with a different kind of excitement. Researchers with the Breakthrough Listen project detected a tantalizing radio signal they named BLC-1. It was not a random blip from billions of light-years away. This one appeared to originate from the direction of Proxima Centauri, the closest star to our own Sun, a mere 4.2 light-years from Earth. What made this signal so compelling were its perfect, textbook characteristics. It was a narrowband signal concentrated on a single frequency, the kind of clean, engineered signature we would expect from a purposeful transmission, not a messy natural event. It also exhibited a frequency drift, a slight shift in its pitch that perfectly matched the movement of a planet orbiting that star. For a moment, it felt like the discovery we had been waiting for, a potential hello from our cosmic backyard. The investigation that followed was a masterclass in scientific skepticism. The initial thrill was met with a rigorous, months-long verification process. Teams across the globe worked to rule out every possible explanation. They checked for aircraft, satellites, and ground-based transmitters. The breakthrough, or rather the letdown, came when they discovered the signal's true nature. It was human-made radio frequency interference, but of a particularly sneaky variety. The signal was not a direct transmission from Earth. Instead, it was likely generated by a piece of electronics on the planet's surface, a device that had malfunctioned or was simply operating. This faint, human-created ripple was then reflected off a piece of space debris or a satellite, bouncing back to the telescope in a way that mimicked the exact drift of an alien world. BLC-1 was not an alien message. It was our own echo, a cosmic prank played by the very technology we built. This episode serves as a crucial lesson. The greatest challenge in the search for extraterrestrial intelligence is not just hearing a signal, but learning how to recognize our own reflection in the vast and silent dark. The search for a true signal is a relentless exercise in separating cosmic whispers from our own noisy chatter. But one candidate, known only by the cryptic name SHB-02+14A, managed to pass the first crucial filters. This was not a discovery made by a lone astronomer in a remote observatory, but by millions of ordinary people. It was detected in 2003 by the SETI at Home project, a pioneering effort that used spare computing power from personal computers around the globe to analyze vast amounts of radio telescope data. This signal emerged from the quiet space between the constellations Pisces and Aries, A point in the sky seemingly no different from any other. What made it stand out was its frequency. It was tuned very close to 1420 MHz, a special number known as the hydrogen line. Hydrogen is the most basic and common element in the universe, and scientists have long theorized that an advanced civilization might use this universal frequency as a logical channel for a beacon, a kind of cosmic watering hole where different species might gather to listen. But SHGB 02 plus 14 was a ghost. It was incredibly faint, and it exhibited a strange drift, meaning its frequency wavered slightly over time. This drift could be explained by the Doppler effect, the same phenomenon that makes a siren change pitch as it moves past you, suggesting the signal source was on a planet rotating at an incredible speed, perhaps orbiting a distant star. The signal was observed only a handful of times and never again with any consistency. Was it a fleeting transmission from a wobbly, fast-spinning world, its broadcast antenna only occasionally sweeping past our line of sight? Or was it merely an unlucky combination of random noise and human interference, a statistical fluke that tricked the world's largest distributed computer? To this day, it remains an unconfirmed but deeply compelling blip, a perfect symbol of the search itself, where the most tantalizing possibilities are often the faintest and the hardest to pin down. Sometimes the most profound mysteries are not heard but seen. A star known as KIC 8462852, more famously called Tabby's star, began behaving in a way that defied all logic. Orbiting our planet, the Kepler Space Telescope was designed to find alien worlds by watching for the tiny, periodic dimming that occurs when a planet passes in front of its sun. But the data from this particular star, located over 1,000 light-years away in the constellation Cygnus, showed something entirely different. Instead of the gentle, predictable dips of a planet, Kepler recorded wild, chaotic fluctuations. The star's light would plummet by staggering amounts, sometimes more than 20%, in ways that were completely irregular and asymmetrical. Nothing in our cosmic playbook could explain how a star could be so violently and erratically shadowed. The most extraordinary explanation proposed was that we were witnessing a Dyson swarm, a vast collection of energy-collecting structures built by an advanced civilization, partially blocking the star's light. This was the alien megastructure hypothesis, and for a moment, it felt not just possible but plausible. The initial discovery, led by astronomer Tabitha Boyajian, after whom the star is nicknamed, sent scientists scrambling for answers. The data revealed two distinct types of mystery. There were the sudden, dramatic dips, like the one where the star's light output fell by a staggering 22%. To put that in perspective, even a Jupiter-sized planet would only block about 1% of a star's light. This was the equivalent of a swarm of objects dozens of times larger than our entire planet passing in front of the Sun. Alongside these sharp drops was a separate, long-term trend. Over the century of data astronomers examined, Tabby's star appeared to be slowly, steadily fading. A natural object large enough to cause such dimming would be incandescently hot and glaringly obvious to our infrared telescopes, which saw nothing of the sort. So what could possibly be both massive and dark? The leading natural theories are intriguing but fraught with their own difficulties. One idea involved a catastrophic family of comets, a vast swarm of icy bodies and debris circling the star in a chaotic orbit. Another suggested a recent planetary collision, leaving a sprawling cloud of fine dust and rocky fragments to occult the light. The most recent evidence points to uneven clouds of interstellar dust, which can dim light without glowing brightly in infrared. But the precise origin and structure of this dust remains a topic of fierce debate. Tabby's star stands as a different kind of cosmic message. It is a signal written in shadows, a reminder that the universe can conceal its secrets not just in fleeting bursts of energy, but in the slow, patient dimming of a distant sun. The alien megastructure idea, while fading in likelihood, served a vital purpose. It challenged our imagination and forced us to ask a profound question. When we see something in the heavens that does not fit our models, how far are we willing to let our curiosity roam before the evidence reins us in? The true nature of this flickering star remains one of modern astronomy's most captivating puzzles. The erratic chatter of cosmic radio bursts had taught us to expect chaos, but then the universe presented us with a clock. FRB 180916 is not just another repeater, it is a celestial metronome. Discovered to have a precise 16.35-day cycle, this signal follows a rhythm so exact it feels almost engineered. For roughly 4 days, it erupts in a storm of powerful bursts, and then, as if a switch is flipped, it falls completely silent for the next 12. This perfect periodicity is a game changer. It provides the first solid, structural clue to what might be causing these phenomenal explosions of energy. The signal's home, a star-forming region in a nearby spiral galaxy, offers another vital piece of the puzzle. It is not located in a chaotic, distant dwarf galaxy, but in a much more familiar stellar environment. This regular on and off pattern points overwhelmingly to an orbital dance. Imagine a dense, energetic object, like a highly magnetized neutron star, locked in a gravitational embrace with a companion, perhaps a massive star. As it travels along its elongated orbit, there is a specific point where it interacts most violently with the wind or the magnetic field of its partner. This interaction could trigger the furious bursts of radio waves we detect, a storm that only becomes visible from our vantage point during that particular orbital phase. The clockwork silence is just as telling, representing the long stretch of its orbit where the conditions for creating these bursts simply are not met. This regularity does not close the case, it opens a new and more focused line of inquiry. We are no longer just staring at random flashes in the dark. We are beginning to trace the outline of the machine that makes them. The universe's clockwork rhythms had already surprised us, but decades before FRB 180916 revealed its precise cycle, another perfect pulse almost rewrote our understanding of cosmic life. In 1967, a young astronomer named Jocelyn Bell Burnell was reviewing data from a new radio telescope in Cambridge when she noticed something utterly bizarre. A tiny, scruffy signal on her chart paper was pulsing with unerring regularity, once every 1.337 seconds. It was so perfectly timed it defied all known natural phenomena. The source, designated CP1919, was so inexplicable that Burnell and her supervisor, Anthony Hewish, half-jokingly nicknamed it LGM-1. LGM stood for Little Green Men. The idea that this could be an artificial beacon, a cosmic lighthouse built by an intelligent civilization, was a serious, if unsettling, possibility. They had stumbled upon a rhythm so clean and precise it seemed engineered. The truth, when it was finally confirmed, was just as extraordinary. They had discovered the first pulsar, a rapidly spinning neutron star. This is the collapsed core of a massive star that went supernova, a celestial object so dense that a single teaspoon of its material would weigh billions of tons. As it spins, its powerful magnetic field funnels beams of radiation from its poles, and if one of those beams sweeps across Earth, we see a flash, like the blinding strobe of a lighthouse in a dark sea. The LGM pulsar was not a message from Little Green Men. It was a natural wonder, a cosmic zombie, the spinning corpse of a dead star. This discovery taught astronomers a profound lesson in cosmic humility. The universe is capable of producing phenomena so orderly and precise that they perfectly mimic the signatures of intelligence we so eagerly seek. It is a constant reminder that our first contact might not be with a civilization, but with a natural phenomenon so magnificent it tricks us into thinking it is one. Every time we hear a strange, repeating signal from the depths, the ghost of LGM-1 whispers a cautionary tale, reminding us that nature itself is the greatest engineer of all. Just a few years ago, it seemed we might have another candidate for a cosmic hello. In the summer of 2016, the Ratan 600 radio telescope in Russia detected a powerful signal that immediately captured global attention. It appeared to originate from a star called HD 164595, a Sun-like star nearly 95 light-years away in the constellation Hercules. This was not a random point in the void. It was a star remarkably similar to our own, a star that could very well host a planetary system capable of supporting life. The signal itself was a strong, narrowband burst, the kind of focused, engineered transmission that fits the profile of a deliberate broadcast. For a brief, exhilarating moment, the possibility hung in the air. Had we finally intercepted a message from a civilization around a twin of our own sun? The excitement was intense but short-lived. The scientific community moved quickly to investigate, and the explanation proved to be far more mundane. The signal's characteristics pointed not to the stars, but to a source much closer to home. The most likely culprit was a military satellite, an object in Earth's own orbit emitting a radio transmission that, from the perspective of the large, fixed Ratan telescope, happened to align perfectly with the direction of HD 164595. It was a classic case of radio frequency interference, a cosmic misidentification. This episode serves as a stark reminder of the invisible web of human technology that now envelops our planet. Our search for intelligent signals is conducted from the bottom of a noisy ocean of our own creation. Every satellite, every radar installation, every passing aircraft creates a ripple that can mimic the very message we are desperately trying to find. The riddle of HD 164595 was solved not with a telescope, but by tracing the signal back to our own front door. It underscores the most difficult part of the search, the constant and humbling task of distinguishing a whisper from the stars from the overwhelming static of ourselves. While we meticulously catalog the fleeting bursts and distant pulses, the cosmos quietly unveils mysteries on a scale so vast we almost missed them entirely. A new class of enigma emerged not from a point of light, but from a ghostly circle in the void. Astronomers call them odd radio circles or ORC. These are not stars, not galaxies, but colossal rings of radio emission, so immense that each one could easily swallow our entire Milky Way galaxy whole. They are not connected to any visible object at their center, floating in the deep fields of space far from the bright hearts of galaxies. When researchers first spotted them, the leading explanation was a shockwave from a cataclysmic event, perhaps the aftermath of two entire galaxies merging in a violent dance. Yet these circles are perfectly symmetrical and strangely isolated, with no sign of the chaotic debris such a colossal collision should leave behind. Another, far more speculative idea whispers from the edges of theoretical physics. Could we be looking at the throats of wormholes, the theoretical tunnels through spacetime, their immense gravitational lenses warping radio waves into a perfect circular mirage? The most profound aspect of the ORC enigma is its newness. These are not puzzles we have been struggling with for decades. They are signatures of something entirely unknown, phenomena we lack the language to even describe properly. It is a humbling reminder that our map of the universe is still being drawn, and the largest structures on the cosmic canvas might only now be stepping into view. That perfect cosmic clockwork is built from phenomena we can at least begin to understand, but some signals defy any easy classification. A new kind of cosmic flash was discovered, one so bizarre it earned the nickname the Cow. Officially catalogued as at 2018 Cow, this event appeared in the sky in June of 2018 as a sudden, brilliant point of blue light. It was not a slow-burning supernova or a gentle stellar flicker. It exploded into view in a matter of days, reaching peak brightness with a ferocious intensity that outshone a typical supernova by at least 10 times. Then, just as swiftly, it began to fade, its brilliant blue light dissolving back into the darkness in a few short weeks. This was a fast blue optical transient, a F-bot, a class of event defined by its incredible speed and its vivid blue color. The spectrum of its light was the real puzzle. It was a chaotic, broad, and featureless mess, lacking the clear chemical fingerprints that astronomers use to identify the elements involved in a stellar explosion. It was as if we were seeing the raw, unrefined fire of a cosmic engine, a blast so powerful it vaporized everything into a smooth, unrecognizable glow. What kind of cosmic catastrophe could possibly produce this? One leading theory suggests it is the birth cry of a black hole. In this scenario, a massive star collapses not with a symmetrical bang, but in a messy, direct implosion. As the star's core gives way, it might fire a jet of material directly out through its poles at near light speed. If we are looking directly down the barrel of that jet, we would see an incredibly bright, fast, and blue flash of light, the brief but brilliant signature of a black hole being born. Another compelling idea is that a star wandered too close to an intermediate mass black hole. The black hole's immense gravity would not just swallow the star whole, it would tear it apart in a violent process known as a tidal disruption event. The shredded stellar material, swirling into a hot, bright accretion disk around the black hole, could produce the intense blue flash and rapid fade we witnessed. Yet the sheer power and the strange light signature of the cow and other F-bot have not been fully explained by any single model. They are a stark reminder that the universe's repertoire of explosions is far from complete. We are still learning the many ways a star can die, and the many colors it can blaze in its final, spectacular moments. These strange bursts and flickers, however, are not the universe's only large-scale mysteries. An even more profound and controversial puzzle lurks in the motion of entire galaxy clusters themselves, a phenomenon astronomers call the dark flow. Imagine the entire cosmos as a vast, calm ocean, with galaxies and clusters of galaxies drifting gently apart on the currents of the universe's expansion. This is the picture we have long accepted. But careful measurements of hundreds of galaxy clusters have revealed something that should not be happening. These colossal structures, each containing thousands of galaxies, appear to be streaming in a coherent direction, as if being pulled by a cosmic tide from beyond the edge of the visible universe. This motion is separate from the overall expansion, a subtle but persistent drift that cannot be explained by the gravitational pull of any known matter. We have mapped the distribution of all the stars, galaxies, and even the invisible dark matter we can detect, and none of it accounts for this flow. It is as if you were floating in a placid lake, yet you and everyone else around you were slowly, steadily drifting in one specific direction, pulled by a current whose source is hidden beyond the horizon. So what could possibly exert such a titanic gravitational influence on matter on such an unimaginable scale? The most mind-bending possibility is that the dark flow is evidence of something entirely outside our cosmic bubble. The pull may be coming from a massive structure in a neighboring universe, part of a vast multiverse. According to some theories of cosmic inflation, our universe is just one bubble in a frothing sea of eternally inflating space-time, with other bubble universes popping into existence beyond our own. If one of these other universes was close enough, the gravitational tug from the immense mass it contains could be reaching across the dimensional divide, gently herding our galaxy clusters like leaves in a wind. This idea pushes the very boundaries of cosmology and physics, suggesting that we are not isolated, but are part of a much grander, multi-cosmic structure. The dark flow remains a hotly debated topic, with some scientists questioning the data itself. Yet if it is real, it points to a cosmos far stranger and more interconnected than we ever dreamed, where the silent signals from the void are not just messages, but the ghostly fingerprints of worlds beyond our own. While the dark flow hints at a pull from beyond our cosmic horizon, another mystery is etched directly into the oldest light we can see. The universe's first photograph is the cosmic microwave background, a faint glow of radiation that fills all of space, a relic from when the universe was just a newborn, 380,000 years old. This primordial map is remarkably smooth, a nearly uniform tapestry of temperature. Yet one region stands out as profoundly strange, a vast and chilling cold spot. This area is significantly colder than its surroundings, a colossal void in the cosmic background that spans over 1 billion light-years across. According to our standard model of cosmology, such a feature should not exist. The temperature fluctuations we see are the seeds of all future structure, the tiny ripples that gravity would later sculpt into galaxies and clusters. But the cold spot is not a tiny ripple, it is a cosmic Grand Canyon. One explanation is that it is a supervoid, an immense and mostly empty region of space. The light traveling through such a void would lose energy, creating a cold imprint. Much like climbing out of a valley requires effort and saps your strength. Yet even the largest known supervoids seem too small to account for the profound coldness of this spot. This leaves a more staggering possibility on the table. Some physicists propose that the cold spot is a bruise, the remnant of a colossal collision between our universe and another bubble universe in the multiverse. In this theory, the energy of that long-ago impact was transferred away from our cosmic bubble, leaving behind a patch of space that is colder and emptier than it should be. A related and equally baffling signal within this ancient light is a strange pattern of echoes, a kind of cosmic boomerang effect. Certain correlations in the temperature fluctuations suggest that some parts of the early universe were interacting with other parts in ways that defy our understanding of its initial, rapid expansion. It is as if ripples on a pond were somehow communicating with each other faster than they could travel. This boomerang signature challenges the very foundations of our cosmological models. If confirmed, it would mean that the story of our universe's birth is incomplete, and that its first moments were shaped by forces or realms we have yet to comprehend. The cold spot is more than just a cold patch on a map. It is a potential window into the multiverse, a silent, frozen signal from a time before time, hinting that our entire cosmos is not alone. The silent, frozen signal of the cold spot is a relic of the ancient universe, but a different kind of messenger arrived in 2017. One that traveled across the cosmos without a sound. On September 22nd of that year, a single, impossibly small particle struck the ice of the South Pole. It was a neutrino, a ghostly subatomic traveler with almost no mass and no electric charge, allowing it to pass cleanly through planets and stars as if they were not even there. This particular neutrino, however, was special. It carried an immense amount of energy, and it did not arrive alone. At almost the exact same moment, observatories across the globe and in space detected a brilliant flash of gamma rays from a distant point in the sky. The source was a blazar known as TXS 0506 plus 056, a monstrous supermassive black hole at the heart of a galaxy 4 billion light-years away. For the first time in history, we had caught a neutrino and a light signal from the same cosmic catastrophe. This was not just a coincidence, it was a cosmic postmark. Blazars are some of the most violent engines in the universe. As a supermassive black hole devours matter, it can fire twin jets of radiation and particles directly into space at nearly the speed of light. We are fortunate that one of these jets from TXS 0506 plus 056 was pointed directly at Earth, making it appear as a brilliant blazar. The detection of the neutrino was the crucial piece of evidence. These ghost particles are only created in the most powerful particle accelerators imaginable, deep within the heart of these relativistic jets. The high-energy neutrino was a direct witness to the ferocious processes occurring near the black hole, a tiny messenger that had traveled for billions of years to deliver its news. This single event confirmed a century-old suspicion, proving that these active galaxies are the long-sought sources of the universe's most energetic cosmic rays. We are no longer just watching the universe's most violent events. We are now catching the very particles they fire across the cosmos, opening an entirely new window into the fundamental forces that shape existence itself. While we chase the high-energy ghosts of neutrinos and radio bursts, a different kind of mystery glows in the dark. Some of the cosmos's most profound secrets are not written in fleeting flashes, but in a constant, warm hum of infrared light. These are the unidentified infrared objects, or UIRO, cosmic enigmas that blaze with light our eyes cannot see, yet remain almost completely invisible in the optical spectrum. They are the universe's hidden embers. The reason for their elusive nature is often a simple one: dust. Vast, dark clouds of cosmic soot can shroud entire stellar nurseries or dying stars, blocking their visible light completely. But this same dust, warmed by the hidden object within, re-radiates the energy as a strong, telltale glow in the infrared. Peering into these dusty veils is like trying to identify a light bulb hidden inside a thick wool blanket. You cannot see the bulb itself, but you can feel the heat it gives off. So what are these hidden power sources? One compelling possibility is a shrouded supernova. When a massive star ends its life, the resulting explosion can be so enveloped by pre-existing dust that the brilliant visual flash is completely absorbed and reprocessed into a diffuse infrared glow. We would miss the spectacular light show, only detecting the aftermath as a sudden, bright infrared object that slowly fades. Another fascinating idea points to the very beginnings of solar systems. A UIRO could be a nascent planet, a Jupiter-like world still coalescing in the disk of gas and dust around a young star. The violent process of its formation generates immense heat, causing it to shine brightly in infrared, even as the thick protoplanetary disk hides it from our optical telescopes. Then there is the most speculative and thrilling hypothesis. Could some of these inexplicably bright infrared objects be the signature of a Dyson sphere under construction? This theoretical megastructure, conceived to harness a star's total energy output, would presumably radiate the waste heat as a powerful, persistent infrared signature. A star that appears dim in visible light, but is surrounded by an object glowing intensely in infrared fits that profile perfectly. It would be the ultimate cosmic engineering project, visible only by the heat it cannot help but discard. The key to solving the UIRO mystery lies with a new generation of eyes. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is our master key to these dusty vaults. It can pierce through the obscuring clouds to see the hidden engines within, distinguishing between a cocooned star, a forming planet, or something far more extraordinary. With every new observation, we are not just identifying strange lights. We are pulling back the curtain on the universe's most secretive construction sites. The universe's hidden construction sites are not always cloaked in dust. Sometimes they are painted across the dark canvas of space in brilliant, silent radio light. A galaxy known as the Dragonfly, or more formally as NGC 3044, unfurls its strange wings in the constellation Sextans. It is a radio galaxy, a class of object typically defined by two colossal jets erupting from a central supermassive black hole. But the Dragonfly is a profound exception. Its radio emissions are not confined to tight, powerful beams. Instead, they form vast, diffuse lobes that stretch across the void, a pair of ethereal wings that give this cosmic insect its name. These are not the clean, focused plumes we expect from a typical active galaxy. They are tattered, ancient, and incredibly faint, whispering of a violent past that has long since quieted. The central engine, the supermassive black hole itself, appears strangely dormant. The galaxy's core is not a brilliant, raging quasar, but a quiet giant. This presents a fascinating riddle. How could such a lethargic heart have once powered such an immense and unusual radio structure? The leading theory points to a cataclysmic galactic merger. Billions of years ago, the Dragonfly might have been two separate galaxies that spiraled into one another, in a gravitational dance of unimaginable violence. This collision would have funneled vast amounts of gas and dust directly into the central black hole, igniting it into a brief, ferocious frenzy of activity. During that explosive phase, it could have blasted out the raw material for those sprawling radio lobes, but the merger also effectively starved the black hole. The chaotic interactions likely cleared out the remaining fuel in the galactic center, shutting down the engine and leaving the radio lobes to slowly fade, like the glowing embers of a long-extinguished fire. Another possibility is that we are witnessing the aftermath of a rare, intermittent outburst from a black hole with an unusual feeding cycle, one that gorges itself and then rests for eons. The dragonfly reminds us that even familiar categories of cosmic objects can hold singular, profound secrets. It is a fossil of a bygone eruption, its silent wings a permanent record of a brief, violent chapter in its life, challenging our assumptions about how galaxies live, collide, and ultimately fade back into the cosmic silence. Deep within the gravitational clutches of a black hole, a rhythm was found. The system known as GRS 1915+105, a stellar black hole devouring a companion star, emits a strange and steady pulse. Astronomers detected it not in radio waves, but in high-energy X-rays, a persistent heartbeat echoing from the very edge of oblivion. This quasi-periodic oscillation is not the steady tick of a clock, but a throbbing rhythm that beats roughly every 50 seconds. A frantic tempo set by the frantic dance of matter in its final moments. This signal originates from the inner edge of the accretion disk, a swirling torrent of superheated plasma that spirals down toward the event horizon, the point of no return. As this incandescent gas is compressed and heated to millions of degrees, it emits the X-ray heartbeat we can detect across the vast interstellar distance. The leading theory for this rhythmic pulse is a fascinating tug-of-war between two fundamental forces. Imagine a powerful magnetic field, anchored in the black hole's rotation, acting like a rigid barrier within the disk. In this model, material from the companion star flows inward, piling up against this magnetic wall. The pressure and temperature build until they reach a critical, explosive threshold. The magnetic barrier is temporarily overwhelmed, and a massive blob of superhot plasma breaks through, plunging into the black hole in a final, brilliant flash of X-ray energy. The barrier then reforms, the process begins again, and the cycle repeats, creating the cosmic heartbeat we observe. This gives us an unprecedented look into the extreme physics just outside a black hole's event horizon. The pulse is a direct probe of space-time itself, warped and twisted by the black hole's immense gravity. By studying its rhythm and its changes, we can measure the black hole's spin, map the structure of its magnetic fields, and understand how these gravitational monsters consume their meals. This single, repeating signal is a natural laboratory for testing the laws of physics under conditions we could never hope to recreate on Earth. These cosmic heartbeats and brilliant flashes all depend on something we have long taken for granted: the simple presence of matter. Yet one of the most profound mysteries in all of cosmology is the case of the missing normal matter. Scientists can calculate with great precision how much ordinary, or baryonic, matter should have been created in the Big Bang. This is the stuff of stars, planets, and you and me. But when we add up everything we can actually see, from the brightest galaxies to the faintest gas clouds, we come up shockingly short. Nearly half of the universe's expected normal matter has simply vanished. It is a cosmic accounting error on an unimaginable scale. For decades, this missing matter was a ghost haunting our models of the universe. The solution, it turns out, was not that the matter was gone, but that it was hiding in plain sight. Astronomers now believe the answer lies in a vast, diffuse web of incredibly hot but thin gas, a structure they call the warm-hot intergalactic medium, or the WIM. This is not a cloud you could see or fly through. It is a superheated plasma, A ghostly fog stretched into immense filaments that form the cosmic scaffolding between galaxies. For so long, this gas was nearly impossible to detect. It is too hot to glow in visible light, yet too thin and diffuse to block the light from objects behind it. It was the universe's perfect camouflage. The breakthrough came from looking not for the gas itself, but for its subtle imprint on the light of distant, brilliant objects known as quasars. As the light from a quasar travels billions of light years to reach us, it passes through these filaments of the WIM. The specific atoms in this superheated gas absorb very particular fingerprints of energy from the quasar's light, leaving behind a series of extremely faint, telltale dips in the spectrum. It is like detecting a specific perfume in a room by the way it has subtly colored the sunlight passing through a window. Each detection is a monumental effort, a single thread of evidence in a tapestry of nothingness. Finding this missing matter does more than just balance the cosmic books. It confirms a fundamental prediction of how our universe is structured. The grand theory of cosmic evolution states that gravity should have pulled matter into a web-like pattern, with dense clusters of galaxies at the intersections and these long, thin filaments of gas stretching between them. The WIM is the final, crucial component of that cosmic architecture. We are finally mapping the invisible roads that connect the islands of galaxies, revealing the true, vast skeleton of the cosmos. The search for the universe's missing matter had revealed a hidden cosmic web, but a more profound shadow was waiting in the void. Drifting through the darkness are phantoms known as dark galaxy candidates, entire islands of mass that seem to be made of almost nothing but shadow. We find them not by the light they emit, but by the ghostly trails they leave behind. Radio telescopes, tuned to the frequency of neutral hydrogen gas, have detected strange, rotating clouds. These vast reservoirs of gas spin with a speed and cohesion that should be impossible. According to the laws of gravity, such a fast-spinning cloud of gas should simply fly apart, scattering its contents into the emptiness. The fact that it holds together, whirling as a single, coherent object, can mean only one thing. It is trapped within an immense, invisible gravitational fist. The rotation implies the presence of a massive halo of dark matter, a hidden skeletal structure holding the entire system together with its unseen gravity. This is a galaxy where the dark matter outweighs the normal, luminous matter by a factor of hundreds or even thousands to one. Imagine a city where the buildings, roads, and people are almost invisible, but the city's immense hidden foundation is what defines its shape and holds everything in place. That is the essence of a dark galaxy. One of the most famous candidates is a cloud of hydrogen called Virgo 21. It appears to have the total mass of a small galaxy, perhaps 10 billion times the mass of our Sun, yet it contains almost no stars. How does something with so much mass fail to ignite the fires of star formation? The leading theory is that the conditions were never right. Perhaps the gas within these dark halos is too spread out, too lacking in the dense pockets needed for gravity to collapse it into stellar nurseries. Or maybe these structures were simply robbed of their stellar potential early on, stripped of their star-forming gas by a close encounter with a brighter, more massive galaxy. Their existence challenges the very definition of a galaxy. Must a galaxy be a place of light, or can it be a place of pure mass and gravity? Finding and confirming these cosmic ghosts is incredibly difficult, as they reveal themselves only through the faintest whispers of radio waves from their hydrogen gas. Each new candidate forces us to ask a deeper question about the nature of dark matter itself. Is it a single, uniform substance, or could there be different types of dark matter with properties that allow some halos to remain completely dark while others blossom with starlight? These invisible giants are the ultimate test of our models, suggesting that for every brilliant spiral galaxy we see, there could be countless dark shadows silently turning in the abyss. Mapping the universe's largest structure requires listening for a whisper in a hurricane. The cosmic web is the grand architecture of our universe. a vast network of dark matter filaments that connects every galaxy cluster in a sprawling, invisible tapestry. For decades, this web has been a theoretical prediction, a ghost in our cosmological models, but now we are on the verge of seeing its bones for the first time. The challenge is almost beyond comprehension. The radio emission from these filaments is incredibly faint, a signal so weak it is drowned out by the brilliant radio glow of galaxies themselves and the constant background hum from our own Milky Way. It is like trying to hear the soft sigh of a breeze from inside a roaring stadium. To even attempt this, astronomers had to combine the data from thousands of hours of observation by the giant meterwave radio telescope in India, stacking the signals to tease out a pattern so subtle it hides in plain sight. The first potential detections are not dramatic images but subtle statistical anomalies, a faint excess glow of radio waves that aligns perfectly with the predicted locations of the web's filaments. This glow is thought to come from the shock heating of the sparse gas within these cosmic threads. As galaxies and dark matter flow along these gravitational highways, they collide and compress the thin gas, energizing it just enough to emit a faint but detectable radio whisper. If these detections are confirmed, it would be a landmark achievement, like developing a new sense. We would no longer be inferring the cosmic web from the galaxies that light up its nodes. We would be seeing the structure itself, the universe's true skeleton. It would allow us to trace the gravitational rivers that have guided the growth of galaxies for billions of years, revealing the hidden currents that shape everything we see in the night sky. That very skeleton of the cosmos is built to receive visitors, and in 2017, a guest arrived from a place beyond our own star. Sailing silently out of the darkness, it was the first object ever detected from interstellar space, a long, dark wanderer later named Oumuamua. Its Hawaiian name, meaning a messenger from the distant past, was perfectly chosen. This was not a local comet or asteroid, but a true interstellar traveler, and its characteristics were deeply strange. Our telescopes revealed it had an extreme, elongated shape, perhaps 10 times as long as it was wide, tumbling end over end through the void. But its most baffling behavior was its motion. As it hurtled away from the sun, something was pushing it, giving it a tiny but consistent non-gravitational acceleration. It was not following a path dictated by gravity alone. For comets, this is common, caused by outgassing, where the sun's heat vaporizes ice on the surface, creating a jet of gas that acts like a gentle rocket engine. The problem was, Oumuamua showed no visible signs of outgassing, no surrounding cloud of gas and dust, no glowing coma, no tail. It was accelerating in perfect silence. This glaring absence of a natural explanation forced scientists to consider extraordinary possibilities. Could the acceleration have been caused by radiation pressure from the sun itself? This is the principle behind a light sail, where a vast, thin sheet catches photons from a star, much like a boat's sail catches the wind. For this to work on Oumuamua, the object would have needed to be incredibly thin and light, a sheet of material only a fraction of a millimeter thick. The notion that it might be a discarded light sail, a piece of ancient alien technology drifting between the stars, was proposed not as a conclusion, but as a serious, if speculative, line of inquiry. The ensuing debate was a perfect storm of scientific intrigue. Mainstream astronomy rallied behind natural explanations, suggesting perhaps it was a fractal-like dust aggregate or a chunk of solid hydrogen ice, materials that could outgas without leaving a visible trail. Yet each theory faced its own hurdles, its own set of assumptions. Oumuamua forced a profound question: how do we classify something that defies all our familiar categories? It was a rock, or a comet, or something else entirely. A cosmic message not in radio waves, but in stone and silence. Its brief passage through our solar system was a reminder that the universe is not only speaking, it is also sending envoys, and we are only just beginning to learn how to read them. A cosmic explosion is supposed to follow the rules. On December 11, 2021, the universe broke them. A wave of high-energy gamma rays swept over our planet, a signal designated GRB211211A. It was a long gamma ray burst, lasting a full minute, a duration that should have signaled the death of a massive star in a spectacular supernova. Astronomers immediately pointed their most powerful telescopes at the spot, fully expecting to see the brilliant, expanding fireball of a stellar collapse. They saw nothing. The traditional supernova signature, the certain proof of a star's death, was completely absent. This was like hearing a massive explosion in a distant city, rushing to the scene and finding no crater, no fire, and no debris. A minute-long gamma ray burst without a supernova was a paradox that threatened to upend our entire understanding of how these colossal events work. The established model was clear. Long bursts come from massive stellar deaths. Short bursts come from the mergers of dense objects like neutron stars. This signal crashed directly through that neat dividing line. So what could produce such an immense, long-lasting flash of energy if not a supernova? The answer appears to lie in the most violent marriage in the cosmos, a kilonova. This is the cataclysmic aftermath of two neutron stars spiraling into each other and merging. As these ultradense corpses collide, they spray a rich soup of heavy elements like gold, platinum, and uranium out into space, creating a brief, hot, and incredibly radioactive fireball. The key difference is in the light show. A supernova is a sustained, bright eruption, while a kilonova is a much faster, bluer flash that fades quickly. When researchers analyzed the fading afterglow of GRB211211A, they found its light curve and color perfectly matched the profile of a kilonova. The implications are staggering. It means that a neutron star merger, an event we thought produced only brief, sub-2-second bursts of gamma rays, is capable of producing a long-duration event. This forces a complete rethinking of the final moments of these collisions. Perhaps the merged object did not immediately collapse into a black hole, but instead formed a rapidly spinning, supermassive neutron star, a magnetar, that lived for nearly a minute, its powerful magnetic field funneling energy into prolonged jets before it finally died. This one strange signal blurs the line between two classes of cosmic explosions, revealing a new pathway for stellar death. It shows us that the universe's most violent finales are not as simple as we once believed, and that the ingredients for precious metals like gold might be forged in more ways and over longer timescales than we ever imagined. While the cosmos screams with brilliant explosions, it also sings with a deep, almost silent bass note. A new kind of astronomy is now listening to this sound, a persistent hum created not by light or radio waves, but by the stretching and squeezing of spacetime itself. This is the gravitational wave background, the collective echo of countless supermassive black holes merging throughout cosmic history. These are not the sharp chirps from stellar mass black holes that LIGO detected, but a low-frequency rumble, a chorus of waves with periods of years or even decades, generated by the most massive objects in the universe spiraling together. To hear this hum, we needed a telescope of impossible scale, so scientists built one out of time and dead stars. They use pulsar timing arrays, networks of rapidly spinning neutron stars that act as celestial metronomes. These pulsars send out flashes of radio waves with a regularity that rivals atomic clocks. As a gravitational wave passes between us and one of these pulsars, it minutely distorts the fabric of space, causing the pulse to arrive a few billionths of a second early or late. By monitoring dozens of these pulsars across our galaxy for years, astronomers can detect the subtle, correlated shifts that reveal the passage of this vast, background hum. Listening to this cosmic symphony reveals a hidden chapter of our universe's story. This hum is the sound of galaxy growth. Every large galaxy, including our own Milky Way, has a supermassive black hole at its center, and when galaxies collide, Their central black holes eventually sink together and merge in a final, violent dance. The gravitational wave background is the statistical sum of all these dances, a direct record of the universe's violent assembly. By measuring the characteristics of this hum, we can census the population of these monstrous binaries, understand how often galaxies merged in the ancient past, and even test Einstein's theory of gravity in the most extreme environments imaginable. We are no longer just watching the silent movie of the cosmos. We are finally turning on the sound, and the universe is humming a song of constant, colossal collision. That deep cosmic hum is the grandest of symphonies, but our own galaxy whispers its own strange and subtle tune. Drifting through the void between stars is a faint, pervasive glow of microwaves that simply should not be there. Astronomers call it the anomalous microwave emission, a mysterious signal that defies every conventional explanation. It cannot be the work of high-energy electrons spiraling in magnetic fields, nor is it the thermal warmth of simple interstellar dust. This is a ghost in the machine of our own Milky Way, a soft murmur that has been confounding researchers for decades. The leading theory to explain this ethereal light is as beautiful as it is bizarre. The signal appears to be coming from clouds of spinning nanodiamonds, unimaginably tiny carbon crystals no bigger than a single molecule, scattered like cosmic glitter throughout deep space. These microscopic gems are thought to form in the cooled atmospheres of certain types of stars, and are then blown out into the galaxy by stellar winds. When these nanodiamonds are hit by ultraviolet light from nearby stars, they begin to spin at incredible rates, billions of times per second. This frantic rotation causes them to emit radiation in the exact microwave band we detect as the anomalous microwave emission. It is a form of quantum clockwork, a precise mechanism playing out on a subatomic scale. Yet the mystery is not fully solved. While spinning nanodiamonds are a compelling suspect, other exotic forms of interstellar dust, like tiny, spinning flakes of carbon known as polycyclic aromatic hydrocarbons, could also be responsible. The challenge lies in the sheer faintness of the signal, and the difficulty of isolating it from the other overlapping emissions that fill the galactic background. This is not a dramatic, singular event from a distant galaxy, but a constant, quiet presence all around us, a background whisper that has been part of the cosmic static for eons. It reminds us that even the most familiar territories, our own galactic home, are filled with unresolved puzzles. The universe is not just hiding its grandest secrets in colossal explosions or dark flows, but also in the gentle, spinning dance of the smallest possible things. Our galaxy holds a final, slow-beating heart. The 25th and final signal on our list is an object that defies the very definition of a pulsar, an ultra-long-period magnetar. Most neutron stars spin in a frantic blur, completing rotations in mere seconds or even fractions of a second, their radio pulses arriving in a rapid, predictable rhythm. This object, however, pulses with a profound and deliberate slowness, its powerful radio beacon sweeping past Earth only once every 22 minutes. It is a cosmic giant breathing in slow motion, and its existence shatters our models of how these magnetic corpses behave. A rotation that slow should mean the star's engine has run down. The mechanism that powers its radio emissions, thought to be driven by the incredible speed of its spin, should have faltered and died long ago. Yet this magnetar's pulses are intensely strong, proving its engine is not only still running but roaring. This forces a complete rethinking of neutron star physics. How can it generate such power at such a leisurely pace? The answer may lie in the unimaginable strength of its magnetic field, the true heart of a magnetar. This field could be so immensely powerful that it acts as a continuous power source, twisting and storing energy like a colossal spring until it finally cracks, releasing a burst of radio waves with each slow turn. We are likely witnessing a star in a transitional state, a previously unseen phase in the magnetic life and death of a stellar corpse. Its slow, powerful pulses are a direct probe into the final stages of a magnetar's evolution, a window into how these incredible magnetic fields finally dissipate and fade back into the silence of space. This single, patient object represents the absolute cutting edge of high-energy astrophysics, a reminder that even among the most extreme phenomena we have catalogued, the universe is always ready to reveal a deeper, more patient kind of mystery. From the fleeting 72-second whisper of the wow signal to the patient, 22-minute heartbeat of an ultra-long period magnetar, we have journeyed through a gallery of cosmic anomalies. We have witnessed the frantic, unpredictable chatter of repeating fast radio bursts, and felt the subtle pull of a dark flow from beyond our visible universe. We have seen stars dim by impossible amounts, and heard the ghostly hum of gravitational waves from merging supermassive black holes. Each of these 25 signals is a unique fingerprint on the cosmos, a singular question mark etched into the data of our telescopes. Yet together, they tell a single, profound story. Our universe is not a quiet, static void. It is a dynamic and often violent arena, filled with engines of unimaginable power and phenomena that defy our current understanding of physics. It is a place where dead stars spin at impossible speeds, where entire galaxies can be made of shadow, and where the fabric of spacetime itself rings with the echoes of ancient collisions. This collective menagerie of mysteries proves that we are living in the golden age of cosmic discovery, where every new observation has the potential to upend what we thought we knew. So the next time you find yourself looking up at a clear night sky, remember this: the silence is an illusion. The cosmos is alive with whispers and shouts, with rhythms and pulses, with messages we are only just learning to decode. The next great signal, the one that changes everything, could be arriving at this very moment, traveling for millennia across the vast dark to reach us. It is a message for all of humanity, and the person who helps unravel its meaning could be you. The hunt for cosmic whispers is about to leap into a new era of unprecedented clarity. Our next generation of eyes and ears are already taking shape. Instruments so powerful they will transform the faintest glimmer into a detailed story. In the remote deserts of South Africa and Australia, a colossal endeavor known as the Square Kilometre Array is slowly awakening. When complete, its thousands of antenna dishes will form a single radio telescope with a collecting area of, as the name suggests, 1 square kilometer. This vast electronic ear will be so sensitive it could detect an airport radar on a planet orbiting a star tens of light years away. It will map the cosmic web in stunning detail, catch fast radio bursts by the thousands, and listen to the universe's radio symphony with a fidelity we can barely imagine. High in the Chilean Andes, the Vera C. Rubin Observatory prepares to conduct its own monumental survey. Its massive mirror and enormous camera will scan the entire visible sky every few nights, not once, but over and over for a decade. This relentless gaze will create the greatest time-lapse movie of the cosmos ever made, catching anything that moves, flickers, or explodes. It will find millions of new transient events, from supernova to asteroid movements, and perhaps spot the next Oumuamua as it enters our solar system. But these observatories will generate a deluge of data, so immense that no team of human scientists could ever hope to sift through it. This is where artificial intelligence enters the story. Advanced machine learning algorithms will be the unsung heroes, working tirelessly in the background to perform the initial triage. They will scan petabytes of data to flag the one-in-a-million anomaly, the strange frequency drift, or the unusual light curve that might signal a new class of object or, just maybe, a pattern that is not natural. This powerful partnership between human curiosity and machine precision will be augmented by a global army of volunteers. Citizen science projects will invite people everywhere to become explorers from their own homes, examining images and data that computers might misinterpret, bringing human intuition and pattern recognition to the forefront of discovery. The ultimate discovery, a confirmed signal from another civilization, has always felt like a distant dream. But for the first time in human history, the tools to make that dream a reality are falling into place. The next strange signal, the one that rewrites all our textbooks, might not be a ghost in the archives or a fleeting blip we struggle to confirm. It could be a clear, repeating, and unmistakable message, its origin pinpointed to a distant world, waiting for us in the data stream of a telescope that is being built today. The universe has been sending its messages for eons. We are finally building the ears to truly